Let's talk about the cache. Now, this is a good topic no matter what. It doesn't, it's not parallel programming specific. This is a good thing for all programmers to know something about, but it does have some especially nasty ramifications on multi-core programming. So, yeah, let's dive in. Okay, so the problem is the path between a CPU chip and off-chip memory is slow. I mean, slow electronically speaking. The chip is sitting over here on the board, the motherboard. The memory is sitting over here, and they're connected with paths on the board. So if the chip wants to go grab something from memory, it has to send an address out the pins. That signal has to travel across the board to over where the memory is, go in the pins of the memory controller. The memory controller then has to fetch out of memory what the CPU chip has asked for, and then that goes back on the pins back to the CPU chip. So yes, this is relatively slow. Um, I've seen statistics that say this sometimes would force the CPU to wait 200 clock cycles, 200 clock cycles where it could be doing something useful. But anyway, this is a huge performance hit. And this was known since the beginning of computing. And so what they ended up doing is they built hierarchical memory systems or cache. And it works like this. They put in some memory on the CPU chip. Okay. The piece of it that the piece of this memory or cache that is closest to the CPU itself, the arithmetic logic unit, is called L1. These caches are named by distance from the ALU. So the L1 cache is closest to the ALU, and the way that they build it electronically is it's faster than the next one. This is L2, but L2 is typically bigger. And a lot of chips have an L3, which is even bigger but slower. So this is hierarchical memory, but it's on the chip. Okay, so if you can leave things here in the cache, next time you need them, you don't have to go out across the board to the main memory. And that's the point of doing this. Okay, again, distance from the ALU, the heart of the CPU chip. L1 is smaller and faster. L2 is bigger and slower. And if there's L3, it's bigger yet and slower yet. Okay, I found some statistics. The Hennessy and Patterson books are probably the gold standard of computer architecture. And I also gathered some information from the internet, from Tom's Hardware, and so on. And so this may not be entirely accurate, but it's pretty close. Okay, so L1, L2, L3 are all on chip, memory is off chip, and disk, well, disk is way over there. Size L1, we're calling it small. 100K bytes is reasonably big, but L2 is really big and L3 is bigger yet. Memory is maybe 1,000 times bigger than what you're fitting on the chip. And of course, disk is just huge. So access time for L1, time to pull something out of L1 memory, is like a quarter of a nanosecond. Now, how big is a nanosecond? Light travels about a foot in a nanosecond. So if I had a flashlight here and I turn it on, a nanosecond later, the light's over here. Um, yes, that's pretty quick. L2, maybe a half of a nanosecond. L3, maybe 10 nanoseconds. And memory, much more. And of course, disk is just ridiculous because it's like way out there. Now, if we scale this, so let's take the speed of L1 and let's just call that 1 second. So we've normalized it to 1 second. L2 would be about 2 seconds of access. L3 would be close to a minute. Memory would be like 3 minutes, and disk would be like 2/3 of a year. So now that's why I like to scale things like that, is it sort of brings it into perspective. Hardware manages the cache. what's in L1, L2, L3. The operating system manages what's in memory and what's on the disk. One thing that I couldn't figure out how to put in the table, L1 is typically two caches. There's typically two L1 caches, one to store instructions. So you're bringing in your program's instructions for execution, and one to store data. And so sometimes if you look at a spec sheet, you'll see L1 cache 32K plus 32K or something like that. And that's what that means. Sometimes they'll just abbreviate it and say IND cache, well, instruction and data. So anyway, you'll see that on spec sheets. Okay, so if the CPU asks for a value from memory, but it happens to live already in cache because you've brought it in once before, that's called a cache hit. And of course, we love that because that is super fast. If the CPU asks for a value from memory and that value is not already in the cache, then it has to go off chip to get it. And that's fairly slow, and that's called a cache miss. Now, to do anything with memory, you're going to have to generate at least one cache miss. But the goal is keep that value in cache so that the next time you get a cache hit. Okay. But looking at this picture of an egg carton, if I need two eggs to make something, I don't go to the grocery store and get two eggs. I go to the grocery store, even though I could, I go to the grocery store and get a dozen eggs because if I need two today, I might need two more tomorrow. I might need four the day after that, and so on. And that way I've got them and don't have to make the laborious trip to the grocery store. So when you ask for a value from memory, the cache mechanism doesn't just bring in that value, it brings in a bunch of values around it. Okay, and that's called a cache line. And cache lines are been 64 bytes for decades. Somebody must have tried it or simulated it or something because through all the new computer architectures, it's always been 64 bytes. So there must be some sweet spot there at 64 bytes, like eggs are always 12. Cache lines are always 64. So thinking about the egg carton again, if I need an egg, two eggs today, I'm probably going to need eggs later in the week. That's called spatial coherence. Okay, if I need a memory value or need a value out of memory and it's right here, chances are I'm going to need this one and this one and this one and maybe this one and this one sometime soon. We tend to, when we say float XYZ, XYZ end up in consecutive memory locations. So if we need X, probably we're going to need Y and Z. And that's why you bring in a cache line. Okay. And so, yeah, this is great. If this is true, now if you need a memory address as contents now, you'll probably need the values right around it soon. That's called spatial coherence. And if that's the case, cache really, really helps. Okay. Temporal coherence is if you need a memory address now or contents now, chances are you're going to need that exact same thing again. I use X here in my program and I'm going to use X down here again. Okay, it's in cache. So yeah, so spatial coherence and temporal coherence are the things that if your program does that, then cache is at its very, very best. Now, if they don't do that, well, then it's like not having cache at all. Okay, let's do an example. So C and C++ store 2D arrays a row at a time. We do this sort of thing in C and C++ to make a 2D array. There really is no such thing as a 2D array. It's a 1D array, but this terminology is convenient for us humans if we want to think in 2D. So if I do this, really all the values are stored horizontally. So The first value in that is stored here, and then here, and then here, and then here. So in terms of I and j, this row is I equals 0. So 0, 0 is followed by 0, 1 is followed by 0, 2, and so on. And so if I need to, say, add up all the members of a 2D array and I do it horizontally, that's great, right? Because they're all sequential in memory. And so, okay, 16 or 64 bytes in a cache line, that would be 16 floats. Well, there's 5, there's 10, there's 15, there's 16. So I can go from here to there without needing a new cache line, which is great, which is really great. This is spatial coherence. Okay, now the moment I ask for this one, I have to bring in a new cache line. So if I was going to add these up, there would be a huge advantage in me going horizontally across the rows. Now, yeah, that's how the code would look. Now, if I go down the columns, well, now I've got a different problem because if I go down the column, so I add this and this one and this one and this one, from loading one cache line, I only get to use 4 of those values. The moment I ask for this one, I'm into a new cache line. If I go horizontally, then I get to use all 16 values. If I go vertically, I only get to use 4. So that's a big waste. So anyway, if you do this and you do it both ways, here's what you get, or here's what I got, is if I do it by row, and this is elapsed time, and I recognize that violates our rule, but I wanted you to see this time gap. So the blue line is if I access by row, the red line is if I access by column, and notice in seconds to do this, how much longer it takes accessing by column. This is a huge, huge difference. It's more than double. So you accidentally access the wrong direction and your code's going to run twice as slowly than if you did the correct direction. So anyway, this is sort of how bad the potential cache problems are. And this is why every programmer needs to know something about cache, regardless of parallelism. Okay, one of the things that I think is always interesting about this is object-oriented programming style can sometimes be inconsistent with good cache use. So imagine we're creating a linked list. Okay, so we have the head of the list and we have a pointer to the next thing and we're storing XYZ values. And every time we need to add a new link in the linked list, then we're going to create a new one. We're going to allocate this from memory, and then we're going to link it in. But the problem is you don't know where these things are in memory. And so potentially this might be the first node in the linked list, and this one might be the second, and this might be the third, and this might be the fourth, and the fifth, and the sixth, and so on. They're all over memory. So the moment you go grab the next node in the linked list, you may be out of your cache line. You probably are out of your cache line and have to load another cache line. So in the worst case, each node is on a different cache line, which is not unusual. So yeah, this is how you're supposed to do it, but sometimes that just flies in the face of good cache usage. What do? Here's what we tend to do if we care about this, is instead of letting the dynamic memory mechanism take care of finding the next node, we create a whole bunch of nodes in sequence, like an array of nodes, and that's where we get the next one from. When we need a third one, we grab this one. When we need a fourth one, we grab this one. And when we run out of these, we allocate another array of nodes on the linked list and link from here to there. Now, eventually, if you start inserting and deleting, they will end up all over memory again. But at least you start out with them being somewhat sequential in memory. okay, which would make things run much faster from a cache point of view. And here's how you would set that up is you would keep that array and then go grab the next thing from the array. Okay, sometimes when we're doing things on bigger data sets, we get a characteristic that looks like this. Like if I'm, say, multiplying two arrays pairwise at a time, well, if I do a small data set size, yeah, I'm not going to get very good parallel performance because of this overhead of setting up parallelism. But as I increase the data set size, my performance is going up and going up and going up. And then oftentimes it starts to drop. And oftentimes the reason is you're violating temporal coherence, meaning I'm only using every data value once. So when I'm pairwise multiplying, well, I'm using these two numbers, one out of the A array, one out of the B array, but once. Then I'm using the next ones, the next ones, the next one. The spatial coherence is great, but the temporal coherence, um, we're not reusing anything. And so sometimes the reloading of the cache um, you have to do it so often that that destroys some of your performance. There is something called prefetching, and there's an entire note set on prefetching, so I'm going to go over it very quickly here. Prefetching means, the idea of, okay, multiply, multiply, multiply up, got to stop now and go get another cache line. What if you could have the hardware go get the cache line before you need it so that it's waiting for you when you do need it? And that's called prefetching. And so if you're doing array times array multiply, if you turn on prefetching, you get performance like this. And if you don't turn on prefetching, you get performance like this. So yes, look at the prefetch notes. Okay, here's another example, which I think is really interesting. When we teach matrix multiply in a math course, in a computer graphics course, we always do it like this. It's three nested for loops, and it has to be three nested for loops. And we always write it like this. It's A I k times B k j, and you sum those multiplies across all the k's, and you get Cij. You get this answer in the ultimate matrix. Okay, so really you're taking this row and this column and pairwise multiplying them together. Okay, and then, that makes sense. And this is typically how we teach it. But in fact, we don't have to teach it that way. Okay, we always write the I for loop, the J for loop, and the K for loop, and put the K on the inside. But in fact, you can permute the order of these for loops and you'll still get the same answer. We just do it the other way because it looks so clean, but you can change the order. Well, if I have three for loops and the order doesn't matter, you get the same answer. That means there are 6 ways I could rearrange the order. And if you do that, here's what you get. Okay, turn your head sideways. So the colored curves here are a number of threads. And across here is the dimension of the matrix, so 200 by 200, 400 by 400. The big winner is the order IKJ. Okay, here's IJK, which is typically the way we teach it. And yeah, that's not bad. Up is higher performance. But notice on the order IKJ, it is like way up here. And notice on the order KJI, the performance is abysmal. This is all due to cache. The IKJ ordering lets you go across rows more often. The KJI ordering forces you down columns more often. But you can see just simply reordering your for loops takes you from around, well, a performance level of 200 to a performance level of over 1,000. And you've not done anything to your code. How long does it take you in an editor to take this for loop and put it down one? Okay, if we invert the curves, we get the same kind of answer. Now the colored curves are size of the matrix, but again, this is the huge winner. And so, yeah, this kind of demonstrates what cache, knowledge will do for you. So again, not necessarily a parallel programming issue. However, so this is the end of the first one. I've broken this into a couple of submodules. The next one, we're going to get into that mysterious thing called false sharing. And that is a parallel issue. I think you'll find that interesting.